Okay, and of course, if you have phones, you can find it. You have walked by it many times on your way downtown. It's a very nice space. And the drill for this thing is like the cookout we had 2 weeks ago. You need your name tag, you get in the front door, and you'll probably get parted at the bar. Okay, I am not responsible for that, but that's the story. Okay, so take it away.
All right, so we're gonna just continue off from where we ended yesterday. So just as a refresher, so far what we've been doing is setting up the first set of assumptions for dark matter, for its distribution in the halo, for its mass, for its interaction strength. And yesterday we pursued the experimental consequences of these assumptions for what are called direct detection experiments, where you're looking for dark matter scattering off of nuclei in detectors. And one of the things that we discussed was that because the dark matter is non-relativistic, most of the predictions that you can make for these classes of experiments, you just need non-relativistic scattering kinematics, fairly straightforward. And then we ended with just kind of a broad overview of what the current limits are from these searches, and the fact that they are starting to probe some very well-motivated regions of parameter space where the dark matter interacts with the nucleus via a Higgs exchange. So today what I'm going to do is discuss two other classes of searches. They're kind of not, it's going to be sort of a part one and part two to the lecture. So the first two, the lecture is going to be divided into halves, and the halves aren't going to be that related to each other. But I think once we get through this today, then you will have had a pretty broad overview of some of the most important experimental efforts ongoing now for dark matter, and then also, just in general for beyond the standard model physics. All right, so part one today is indirect detection. And what these class of experiments are looking for are interactions of the dark matter in the Milky Way halo. So here's our halo. Here's the disk. Here's the sun, and the galactic center is there. The idea is that there's dark matter particles zipping around all over here. And while their self-interactions are very small, every now and then we do expect that they will find a partner and maybe annihilate with each other. So you will tend to get some self-annihilations, especially in regions of high density. And so the purpose of these types of experiments is to look for the standard model products that you would get from these annihilations. One of the probably leading experiments right now in this is the Fermi satellite. But then there's also a lot of Cherenkov telescopes, sort of ground-based telescopes, that are also looking for this. All right, so what do you actually measure in this case? Well, what you're looking for is a flux of gamma rays. And so the important quantity is this flux as a function of the energy of the gamma ray that you're seeing and the direction in the sky at which you're seeing it. So one thing that you do hope to do with these kinds of experiments is to reproduce the spectrum of the annihilation products as well as the spatial distribution on the sky. So this flux is just related to the velocity averaged annihilation cross-section. There's just some factors here, the denominator. It gets multiplied here by a photon spectrum, which I'm going to describe in a second in some more detail. And then there's an integral over the line of sight that depends on the density of the dark matter. And I want you to tell me what the exponent of this should be. What I'm looking for here, remember, is two dark matter particles that find each other and interact. So should this exponent be 1, 2, 3, or higher? 2, good, awesome. And if it was, because we can also do the same exact thing except not looking for annihilation and instead looking for dark matter decay. If we were looking for dark matter decay, what would the exponent be? Yeah, good. All right, everybody's awake. All right, so just to be clear about what exactly I mean by doing this integration over the line of sight, just remember what the geometry is. So if here is the galactic center, so the black hole at the galactic center, and here we are at the position of the sun, and let's say we observe photons that are coming to us from some point elsewhere on the sky. This gamma source is some distance r from the galactic center and some distance L from the sun, and where this L is oriented by some angle psi from the line that's connecting the sun to the galactic center. So we're doing this integral of flux. When we're doing this integral of flux, we're integrating the density that we observe along this entire line. Because from our perspective, we actually don't know whether or not the gammas are coming from here, here, or here. We just know that we see it when we point our satellite in this direction on the sky. So that's why we have to do the integration over the entire line of sight. Okay, so there's a few interesting signatures that we can expect to see, and it depends entirely on what the dark matter annihilation modes are. So let's start off by just considering what happens when the dark matter annihilates through some mechanism that we'll just remain agnostic about, and gives us standard model final states that can look like W bosons, Z's. We can get quarks, electrons, anything like that. So in this case, the photons that we observe are actually going to be, they're referred to as secondary photons. And they're secondary because they're not the what's immediately produced by dark matter. You end up getting the photons from emission of these guys. So in particular, if I were to produce a W boson to a pair of W bosons, the W's will then, they can decay hadronically to quarks. The quarks will radiate off gluons. It starts becoming complicated. You end up getting a collection of quarks and gluons in this showering process. So you get a QCD shower here. And then you end up forming pions, mainly pions, from all of the quarks and gluons that have that have been produced in the shower. So then you end up with a bunch of so this process is called hadronization, where you end up with these pions, and then the pions decay to photons. So you only get the photons that are at the end of this showering and hadronization process. They're not coming immediately from, they're not an immediate annihilation product from the annihilation here. That's important mainly because it does affect, what the energy of the photons that we expect to observe. And the way this feeds into this flux is with this factor here, the photon spectrum. So for example, let's see if I have enough space here to sketch this out. If I make a plot of photon spectrum where I'm plotting this in terms of energy of the photon divided by mass of the dark matter, and this is 1. So if I have dark matter annihilation to WW, the photon spectrum looks something like that. Yeah? Because that's what's going to happen most dominantly. It will also decay leptonically, and you will get some, you will get some photons that get radiated off the leptons. But this is what ends up giving you the dominant contribution. Yeah. Okay, so let's say this is the distribution, the energy distribution of the photons you expect to get from annihilation to WW. How would this line change if I had annihilation to ZZ instead? Would it look more like, would it look more like this? So that would be option A. Option B would be it looks exactly like WW. Or option C would be something like that. So let's see, as a hint, if I produce ZZ instead, the dominant decays of the ZZ would be to what? To what? Oh, no, Z doesn't go directly to gamma. So the dominant branching fraction of the Z would be hadronic as well. Okay, so so Z would be hadronic. It would go just to the same flavor, quarks. Okay. So how do you think that would affect the shower? This may be a trick question. It actually doesn't affect it. It looks the same as if it was from W's. And the reason is because the shower doesn't really care whether or not you've initially produced two quarks that are the same flavor or not the same flavor. The process kind of continues as it would have for production of W's. So for ZZ, it actually just looks like the same curve as for WW. If I were to just produce quarks instead, just directly produce the quarks, do you think it would change? So it turns out it doesn't actually change by very much. It's effectively still very similar, just because the spectrum really gets dominated by this showering. Where things do change a lot is if you were to produce leptons instead of quarks. So if the dark matter annihilated to electrons, then, or let's say taus, then you'd end up getting a very different distribution. It would look more like this. So this would be, for example, what you'd expect if you annihilated to taus. Like something like what? Oh, no. Just because you tend to get more photons from taus, but it's actually not very different for electrons either. So electrons, muons, and taus will look similar to this. You just tend to get more photons at high energy, and then W, W, Z, Z, and anything to quarks all ends up looking roughly the same.
So the detector sensitivity accesses only the photons and not the charged particles?
So the Fermi satellite's only sensitive to photons. Things like AMS are sensitive to charged particles. Yeah. So it does depend on the actual experiment.
So what about a situation where it goes directly to photons?
Oh, I was going to get to that in a little bit. Yeah. Okay, so if we have it go to any of these modes, what we would observe in terms of the flux is something like this. So our satellite's up there, and it's collecting all of these gamma rays, and it's measuring the energies of these gamma rays. And we have, actually, let's just do counts, because we're just literally counting up every photon that hits the detector with a certain energy. And the background I'm going to be kind of agnostic about, but it looks something like this. And the signal for this case would look like that. So it's referred to as like a continuum signal because it's spread over a wide range of energies for the photons. And you can see why that would be the case primarily from this, because you end up getting photons that are spread over a wide range of energies from these kinds of annihilations. So you'll get much more striking features if the dark matter annihilates directly into photons. So in that case, we'd have something that looks like that. Okay? And now the photons are coming directly from the annihilation of the dark matter. We don't have to rely on any of the showering. And this ends up giving a very clean signature. And to see why, let's just do some of the basic kinematics here. So again, the dark matter is non-relativistic in this case. So we can treat this as two dark matter particles coming in, but they're essentially at rest. And then they annihilate to give us, let's say, two photons, or I'm even going to do this a little bit more generally and say a photon and some other particle. It could be a Higgs, could be a Z boson, could be something like that, could be another photon. So in this case, the 4 vector for the photon I can just write as k cosine theta, k sine theta, where theta is just that angle. And the 4 vector for this guy is just going to be similar. It's just going to be the energy, and then minus k. And if we just demand energy conservation, then we find that twice the mass of the dark matter is equal to the energy of the photon plus the energy of the other particle that's being emitted, which is just going to be k squared plus the mass of the other particle. So we can just solve this out for k. So k is just essentially, right, that's just the energy of the photon. And to first order, this gives us that the energy of the photon is equal to the mass of the dark matter times 1 minus mx squared over 4 mass of dark matter squared. Okay? So I'm going to remake this plot now, but for the case where the dark matter annihilation is into photons. So what is the if the dark matter annihilates to 2 photons, what is the energy of the photons? It's just the mass of the dark matter. So it's a monochromatic photon line. So let's say here's our background. If that was the annihilation mode, we'd expect to see something that looks like that. A peak right at the dark matter mass. If the dark matter annihilated into a gamma and a Z boson, I would also get a line. Would that line be above or below this one? Yeah, people are kind of pointing. Yeah, it's going to be below. So I could get something like this. So this would be the gamma-gamma line, or I could get a line for gamma-Z annihilation. So for a long time, people referred to these line signals as being the smoking gun signature for dark matter, because the shape of the signal is so different from the shape of the expected background that if you were to observe a line, it would be really hard to argue that it's being faked by some unknown astrophysical background. I think people hesitate to use that smoking gun terminology anymore because a few years ago there was a observation of a gamma ray line in the Fermi data, and everybody got really excited. It would have corresponded to a 130 GeV dark matter candidate. Oh, yay, we model build. Everybody got really excited. And then it turned out to be some kind of probably a systematic in the Fermi analysis that I don't even know we fully understand right now, but the significance of the detection has gone down and it looks like it's going away. So, no, it's not even astrophysics. It's a mess. Yeah, so it was, one of these kind of waking up moments when you realize, like, yeah, even seeing a line, you have to be really careful because things like that can vanish. The ideal kind of pie in the sky, like dream big scenario is if we do observe dark matter annihilation, it likely is annihilating in more than one way. So some fraction of the time it'll go directly to photons. Some other fraction of the time it might go to WZ or something like that. And what we would actually observe is, something that might look like, we'd see a bump here coming from, let's say, annihilation to WW. And then we'd also resolve these little peaks at the end coming from the annihilations to gamma, gamma, and gamma Z. Or, just depending on whatever the annihilation modes are. And effectively, we'd be able to do spectroscopy. Essentially, by comparing the relative heights of all of these different contributions, we'd be able to infer what the relative branching fractions are of the dark matter to each of those modes. Yeah, so this is sort of the pie in the sky goal. We'd be extraordinarily lucky to be able to do something like that. And so far, the data hasn't really been cooperating. Yeah, let's see. Oh, one other thing I did want to mention is that while these annihilations to gamma, gamma, and gamma Z are give you these lines and are really great in that respect. In general, the lines tend to be loop suppressed in many theories. So, for example, in SUSY type scenarios where you have neutralinos and charginos, you get WW annihilation at tree level from chi-chi and then with the chargino exchange. But annihilation to gamma-gamma only occurs at loop level. So you'd have chi, let's see, make sure I get this right. Oh, no. Get W exchange, and then you get charginos. You get a box of them, and then you get the photons coming out. So the rate for these line signals tends to be suppressed, usually by loop factors relative to what you get from the continuum signal. Yeah? No, it's actually more dominated just by the resolution of the instrument. Oh, the ideal, yeah. 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 Okay. And the last point I wanted to make on this was that there's also considerable astrophysical uncertainty in the interpretation of any signal. And the astrophysical uncertainty is coming from our lack of knowledge of just the dark matter density. So on Monday, I told you that, so this is on a log-log scale, log and log. Many simulations tend to find curves that look like this, which we refer to as NFW, for the dark matter density. Others will find, let's see, there's another common one, which is INASTO, which looks actually very similar to the NFW, but you can have more dramatic variations. For example, scenarios where the density profile is chord. So where there just isn't as much stuff near the center of the galaxy, and that would decrease the strength of any signal that you might expect to get. So whenever interpreting any of these signals, because the flux depends on rho squared, you become sensitive to all of these uncertainties. Let's see, how am I doing on time? Oh, great. Okay, so the last part I wanted to just talk about with indirect detection is kind of where our status is now with experimental searches. So the strongest limits right now come from observations of dwarf galaxies. So these are dark matter dominated galaxies. They don't have a lot of stars. There's not a lot of baryonic physics that's there. So these are considered really clean systems to look for dark matter. Essentially, you point your satellite at a region of the sky that's dark, and you just stare. And you hope that you would end up, as you gain exposure, you hope you'll end up picking up some signal after some amount of time. And so this is what people have been doing with Fermi. There's about 24, well, I guess there's more now, on the order of 30 dwarfs that we have actually observed. About 15 of these have better measured profiles. So most of the limits are coming from these 15. And current bounds, I can't increase this, are usually plotted with the mass of the dark matter on the horizontal axis and the velocity average cross-section on the vertical axis. The current bounds will depend on the annihilation product. So I'm going to just show you what the limit is for annihilation to BB bar. But for example, for annihilation to WW and ZZ, it's not very different from this. And so let's see, everything above this line is excluded. And the most important thing to take away from the current dwarf bounds is that for a dark matter mass of 100 GeV, the current limits for the cross-section are roughly 3 times 10 to the minus 26 centimeters squared, which is the annihilation, the thermal annihilation cross-section for dark matter. So this is an interesting value because this is what you would expect the annihilation to be if you were to have freeze out. So the fact that the results are telling us right now is that the current limits are actually excluding scenarios where the dark matter mass is less than 100 for the freeze out scenario. So yeah, I mean, there's a 95. I mean, this is the mean. Let me see. This is actually a band, so there's like a 95% containment. But the mean exclusion is here, and so it's starting to get quite tight on excluding. I mean, this is essentially the sweet spot for WIMP, right? Remember we said we're starting to look under the lamppost. We're looking for weakly interacting dark matter, freeze out, thermal annihilation. That's the sweet spot. And the limits from these experiments are getting so good right now that they're starting to say something about that sweet spot. Yeah, so so the limits that are presented are, they stack all of the limits from all of the dwarfs. And yeah, if you look at other annihilation channels, some of them are weaker. So like the leptonic annihilation channels, the limits are weaker than this. And there is, I mean, these limits are all depending on whether or not we've actually determined accurately what the density is for these dwarfs, and there is a considerable uncertainty in that as well. So yeah, that's a good point. There are there's caveats to this, but suffice to say that the experiments are starting to get to a point where they actually are touching / getting close to interesting regions that we have to then, as theorists, take this back and rethink possibly what the implications are for the models. So this is the dwarfs. Where else might be a good place to look for dark matter in the galaxy? We want to look at places where the density is really high. Yeah. So the other place we'd want to look is in the galactic center. And this is where things are really confusing right now. And the reason is because there's an excess that's actually observed in the center of the galaxy. So the energy of the photons, well, it's usually plotted E squared the NDE here, but it looks roughly like this. This is with background subtracted. So just the excess. There's a peak here around 2 GeV. This isn't a statistical fluctuation because there's a lot of photons that are observed here. It's about 10% of the flux from the galactic center. It's thousands of photons that we're observing. So for sure, this isn't. I mean, I think if you were to actually try to, put in the numbers and get a sigma, it's like a 40 sigma signal. But the issue is that the galactic center is incredibly complicated in terms of the backgrounds. And this, this figure I've shown here is making an assumption that we've done our background subtraction properly. And because we don't understand the galactic center that well, it's very, very possible that there are other astrophysical phenomena that we don't know, aren't very well characterized, that aren't being properly modeled, and so aren't being subtracted from this. I would say this is pretty hotly contested, and depending on who you talk to, you'll get different opinions as to whether or not they think it's dark matter or not. There's been a lot of model building that's done on it. I actually think it's not dark matter. I just actually had a paper on this where we think it's some other astrophysical contribution. But suffice to say, very interesting. There's probably going to either be some new astrophysics or some new particle physics that's going to come out of this. And if it is a background that we don't understand, then we need to kind of get at the heart of it so that we can continue searching for dark matter in the center of the galaxy.
What
Yeah?
kinds of normal astrophysical processes do you reach energy cycles?
Pulsars. And actually, so if I were to just draw the expected energy spectrum of photons from pulsars, it would look something like this. Now, people who think this is dark matter will argue that the difference is coming mainly from here. That's what's distinguishing the two scenarios. The issue is that the error bars here on the signal are quite large, so I would argue that it's actually not that inconsistent. But yeah, it's a really, really messy place in the sky to try to observe things in. Yeah. Yeah, that's another good question. Yeah, so we don't know, right? Because the flux again is sort of this integral over the line of sight. It's most likely dominated by stuff that's fairly close to the center. If you look at all of the photons coming from this, they are contained within about 10 degrees of the galactic center. And their morphology is spherical, so it actually looks It actually, the morphology of the signal actually looks like what you'd want a dark matter signal to look like. It's spherical, and it extends off the plane by quite a bit. You would know pretty much that it's not dark matter if the signal was following the galactic disk, because that, our NFW, the dark matter shouldn't know about the disk, right? So it should extend roughly the same amount in all directions. Yeah. So that's pretty well understood. That's another reason why the pulsar explanation is people just don't understand is because most of the observed pulsars that we have seen follow the disk and aren't going off the plane. So that's why I was saying, like, regardless of what it ends up being, it's going to be something new. It's just, the question is it dark matter? Because that would be extra cool. Yeah.
What's the name of this experiment?
This is Fermi. Yeah, and also if you were to fit this with a dark matter signal, it's fit very well by about a 30 GeV dark matter, annihilating the BB bar. It would be roughly here on that plot. So it's sort of in this nebulous region of where we can't tell whether or not it's been excluded by dwarfs, but maybe excluded by the dwarf limits. Yeah?
I was just wondering, so I know background subtraction is also really important for direct detection.
Yeah.
So could you compare like the challenges for the two? Is there like?
Oh yeah, that's a good question. So the backgrounds are very different between the two. So in this case, most of the backgrounds are coming from cosmic rays. So, for example, if I have a really high energy electron and it's zipping by some gas cloud, it'll brem. So you'll get some photon that just gets radiated off. Or if I have boosted pions, they'll decay to photons, and that, so you get most of the background here from cosmic rays, and that's sort of a developing field in and of itself, just how to model these cosmic rays. So that's kind of the challenge with this. With direct detection experiments, a lot of the backgrounds come from radioactive contamination, which is why you have to put you put these experiments deep underground, both to shield out cosmic rays coming through the Earth's atmosphere, but then also in like clean rooms and things like that to try to decrease the amount of radioactive material that's there. So I was telling somebody yesterday, but a few weeks ago I was at this conference where the CDMS experiment, which uses germanium, was talking about how they are like trying to deal with all their backgrounds. And this person was up there giving this talk and saying that they've been debating, like, this is how detailed they need to be. They've been debating whether or not to ship their crystals via airplane or via ship, because the amount of exposure that it would get to cosmic rays is different. So they're doing this cost-benefit analysis to try to figure out like just how much radiation they can deal with, down like to that level, which I found just astounding. So yeah, trying to like decrease all of this contamination is really hard for those kinds of experiments, but very different type of backgrounds to this.
But I don't know. Is one of them kind of like easier to like kind of experimentally really hard to get rid of the background?
Yeah.
But then maybe
I think I would argue that the modeling for the cosmic rays is more challenging and probably has a longer road to go just on the theory side, like us just understanding what the possibilities are and then seeing whether or not we can constrain some of the models with experiment. I think that the physics for the backgrounds associated with direct detection is better understood. It's just a matter of like being really careful and making sure that we've caught all of the radioactive backgrounds and things like that. But for the cosmic rays, it sort of feels like there's actually just some fundamental physics that needs to get worked out. Yeah. Yeah.
how long until you're like more confident that block is pulled out?
Yeah. It's probably, so the sensitivities actually currently with Fermi are, they're going to improve, but not dramatically, and it's actually unclear whether or not they'd end up improving so much that it would say something definitive about this blob. What would change things dramatically is if we discovered new dwarfs. So that would, that's essentially the thing that you'd really want to do, is find an additional dwarf galaxy that we just haven't observed yet. It's in some region of the, it's close, it's nearby, it ends up being a perfect place to look for dark matter. And that kind of discovery could drive these limits down very quickly. And the possibility for that is strong, because right now we haven't even looked over the whole sky for dwarf galaxies. We've just been limited by the search regions of current, like SDSS and DES. And so I think that's something that with, Dark Energy Survey, just with, their first run, they were looking in a different region of the sky and they discovered 8 more. So I think as more of the sky is covered, there's a good chance that we might end up finding something that serves as a good target. Yeah. Oh, yeah, he had his hand up first.
Is there some robust way of relating the chi cross-section with the chi nucleon section?
Yes, yeah. Yes. I'm going to kind of make a comment on that later when I discuss the collider searches, because there's a way of relating all of these together.
How can it be robust? It depends on the particularity, the particular model.
Yeah, so you can't make it completely robust, but there's you could either do the comparisons by just writing down effective theories for the dark matter interaction. You can also do it using simplified models, which I'll give an example of in a little bit when I do the collider stuff. Yeah.
So the data on the left is just coming from the Milky Way Center?
Yeah, this is from the Milky Way Center. Yeah, so, I mean, if this were dark matter, what you'd really want is see a hint in the center of the galaxy, and then go look at dwarfs and see it there too. Yeah. Are there any other questions on the indirect stuff? Because otherwise I'm going to totally change gears and do some collider overview. Oh, yeah. So this is a separate signal that I haven't described here. Yeah, no. I'll mention it briefly because it's it's a 3.5 keV X-ray line that's been observed in some galaxy clusters and could potentially be consistent with, let's say, a decaying sterile neutrino. So it's caused some excitement because, it could be this dark matter signal. I'm kind of just waiting on that one because the fact that they see it in some clusters and not in others is a bit concerning, and so it makes me wonder whether or not they're just not fully understanding the lines that they're seeing. But at least with that, there should be resolution soon because there's this Astro H satellite that should go up, have a better resolution. We'll just look at the same target and we'll be able to tell us for certain. I haven't heard anything terribly convincing, but yeah. All right. Well, if there aren't any more questions, I'm going to completely switch gears and talk about colliders and how we can look for dark matter there. Actually, maybe I'll just go on the third set of things. OK, good. All right, so part 2, collider searches. And so this kind of came up before, but the reason, collider searches is going to finish off our kind of exploration of dark matter searches. So if we draw a diagram that's dark matter, standard model, what we've just explored now is what happens when we go in this direction. So that's indirect searches, right, where we have dark matter annihilation, and we observe standard model. Yesterday we considered what happens when we go this way, which is dark matter scattering off of standard model, some nucleus, and scattering off. And so this is direct detection. And collider searches is going to finish this off for us because it's going to pull us, it's going to go that way. So for example, at the LHC, we're looking for proton-proton collision, and we're checking to see if we can produce the dark matter from that. And so related to the question that was asked before, it is feasible to write down some, let's say you write down some effective field theory that describes the interaction between dark matter and standard model. You should very easily be able to use that same operator that's going to describe going this way versus going this way versus going that way. So any limit that you would draw from an indirect detection experiment, you could then end up relating to direct versus collider. All right, so what do we actually, what actually is a collider experiment searching for? So we have the best collider experiment ever right now running. So run 1 of the LHC, which ended, I guess, last year, was running at an 8 TeV center of mass energy, proton-proton collision. Run 2 of the LHC, which they've just started getting beams, I was about to say orbiting, circling, is going to have a center of mass energy at 13 TeV, so big jump in energy. And data from this run we expect will probably start trickling in end of this year, and that'll probably, what they'll do first is just try to reproduce results that they've gotten with run 1, and probably by this time next year we'll start getting new results just in terms of, new limits, possibly new discoveries, hopefully new discoveries. Okay, so at a collider, right, these protons are getting accelerated in these large circular rings, and then they collide at certain points, and we put detectors at those points. And then the detector is meant to find all of the stuff that comes out of those collision points. So I'm just going to draw a little cross-section schematic for CMS. So there's at the LHC, there's 2 different detectors that are focused on BSM physics. There's the CMS detector, and then there's also ATLAS. And their design is different. They're essentially competing experiments, the idea being that they can cross-check one another. So I'm going to look at the cross-sectional area of the CMS detector. So if I were to look at a slice of the detector like that, so here would be the interaction point. So the point where my protons have collided and I produce some new physics. The first region that extends roughly about 1 meter from this interaction point is a tracker. And what that tracker does is it can actually tell the direction of any charged particle. After the tracker, there's an electromagnetic calorimeter. So for example, if an electron is produced at this interaction point, it would be observed as a curved track here, and then it would deposit a ton of energy in this electromagnetic calorimeter. So this would be an electron. If instead a photon were produced at the interaction point, you wouldn't actually observe it in the tracker because it's not charged, but then it would deposit a bunch of energy here in the electromagnetic calorimeter. The next stage is it's called the hadronic calorimeter. And this is where we catch all of the mesons that are produced in the interaction. So if I produce a quark and then it hadronizes, so I get some pion or something, we'd see a track here, and then it would get stopped here in the HCal. The one thing that doesn't get stopped at any point here is a muon. It just travels right through. You could send a muon through tons of lead, and it just doesn't get stopped. And so you then need to put something here at the end, which is to catch the muons. And it's like blocks of lead at the end. So a muon would just kind of travel through and wouldn't get stopped until it goes far out. This is, extends out to 7 meters from the interaction point. So huge detector, layered like an onion, where each layer is designed to catch different particles. It has to do with the material that's used here, and so I don't know the specifics, but it's essentially that the stopping power is going to be much. These guys are strongly interacting, Yeah, so actually I don't actually know what the difference is between the materials. Yeah. Yeah, even charged pions will go through the ecal. Yeah. So what would happen if we produced a dark matter particle in the interaction? Where would that get caught? Yeah, it wouldn't get caught. It would just go right through, and we wouldn't see anything. And so the signature for a neutral particle is just missing energy, because you know what your total energy is, and you know what the total visible energy is. And so you can compare those two, and if there's a disparity between it, it would be indicative of possibly dark matter or something else, because there would be some missing energy that you'd see. Oh, yeah, yeah. Oh, I think it's squeegee time. Okay. Well, if there's any questions I could take during squeegee time, that would be great. Yeah? It's not, actually. The way we see neutrinos is also as missing energy. Yeah, so we wouldn't really know if we do see missing energy whether or not it's neutrinos or, well, we'd be able to determine based on like spectrum and things like that. But yeah, in some sense it's degenerate with neutrinos. Sorry? Yeah. So everything that we measure is just the transverse. Yeah. So the way I'm going to kind of summarize the limits that we have from current LHC searches, I'm going to be using terminology from supersymmetry. So I'm going to be talking in that context. I think, Ricardo, you're going to actually talk about supersymmetry, right? Next year? After this is going, right? Okay, so yeah, because what I ended up just figuring I would do is just give you a field guide to particle names. So just enough so that you can follow what I'm going to say today, but that you'll end up getting the full discussion, hopefully later this week. Oops. Okay. So, you know what? Maybe I'll do this here so that it goes up there. All right, so here's our field guide to SUSY, simplified version. Right, so in SUSY, every standard model particle has a superpartner with opposite spin statistics. So for example, if for the quarks, their partner is a squark, so the squark has the same quantum numbers as the quark, except it's a scalar rather than a fermion. And we usually denote these, the superpartners with tildes. The superpartner for the lepton is the slepton. I think you've probably figured out the pattern by now. All right, then for the bosons, we have the W, the B, and the gluon. Their partners are going to be Wino, Bino, and gluino. Oops. Right, all of which are, these ones here are fermions. And I kind of ran out of space, but I'm going to squeeze in the Higgs down here. In the MSSM, we need 2 Higgses, so it's like a 2 Higgs doublet model. So 1 Higgs up, Higgs down, and their partners are fermions that are called Higgsinos. Okay, so that's the field guide for our discussion to follow. Now, if you write down any model for supersymmetry, there's a ton of free parameters. It's like over 100 free parameters. And so you immediately run up to the challenge of figuring out a way that you can interpret any experimental bound in terms of all of those parameters. So one option is you can just do huge parameter scans, like get some big computer, churn it, look at all possible combinations of the parameters, see what's ruled out, see what's ruled in. Another option, and this is what I'm going to do here, just because I think it's helpful in terms of just gaining intuition for what's going on, is to work with what's called simplified models. So in the simplified model approach, you have some TeV scale Lagrangian so some SUSY Lagrangian, for example, except you only include the particles that are relevant for the observables. You assume that everything else in the theory is integrated out. Now, obviously, this isn't a complete theory. This is essentially just a means at, it's a first step, right? If you're running an experiment, these are the kinds of, they're toy models that you could use as a way of just gaining some intuition for what the experimental results are telling you. And then if there is a discovery, then you would generalize these models to more complete theories. So I'm going to start off with, in order to describe our current status of searches, a supersymmetry-inspired simplified model. And for now, let's consider the scenario where everything is integrated out. All the squarks and the leptons are heavy. And so this is energy. The only thing that's kept light is the dark matter candidate, which I'll tell you exactly what that is in a moment, and its charged partner. Okay? So the dark matter particle in these SUSY models is a Majorana fermion. It's the neutralino. And it is essentially just the mass eigenstate of the linear combination of the gauginos and Higgsinos. So I'm just going to write that down as follows. So linear combination of the superpartners for the Higgs and the superpartners for the W and B bosons. So these guys just all end up mixing, and they give you a neutral particle that actually works really well as a dark matter candidate. The charged components of these fields also mix. And so this is the neutralino here. That's the neutral component, obviously. And then the charged one is called the chargino. And it is a linear combination of just the charged bits. So A1 plus or minus plus A2, and then the charged component of the Higgs. Okay? Sorry? It does. The charge, the W? Yeah, gluino's colored, so it won't mix. Yeah. Yeah.
In a scenario like that, for instance, we're going to look at must be something specific. You want to have this kind of slide that you can sort of put that part of the
Yeah.
wouldn't you have you also have the neutral. So you have the you also have the neutral the
Yeah. I was yeah, that's a good point. Yeah, so I was being a little glib. There's going to be 4 of these guys. And the lightest one is the dark matter, but you can also have another light one that has mass that's similar. It's also there. And you can also have 3 others, yeah, which we can drive the other 2 high.
This is the smallest package.
Yeah, this is the smallest package. Yeah, so you have your dark matter, the lightest neutral guy, the second neutral guy here, and then your charged one there. So for now, I've separated everything else out because I just want to think about the physics that's associated with producing any of these neutralino guys. Okay. Go a little bit faster, but I think we'll be able to get through the most important bounds. So the way that these neutralinos interact with the standard model is either through the Higgs exchange, through Z exchange, or W exchange. And which diagrams dominate depends specifically on the mixture, the details of the mixture there. But one place that we can look for these things, these neutral guys, is in Higgs decay, right? So we've discovered a Higgs, and maybe this Higgs is actually also coupling to supersymmetry, so to some of these neutral guys. So if we study the heck out of this Higgs particle that we found, and we see any deviations from the standard model properties, it might just point to some new physics. And it's pretty amazing that already just in run 1 at the LHC, where we've just discovered the Higgs, but we already are starting to get good enough measurements to actually start saying some interesting things about whether or not it communicates with these other models. Okay, last squeegee. Can you also have the what? Yes, yeah, and that could also be a dark matter. So in some models, you get it's this neutrino, yeah. Is it? Is it totally ruled out? Oh. Well, yeah, if it couples only through the Z, then it would be, yeah. Yeah. Yeah, because then it would be 10 to the minus 39, then it would be totally excluded. Okay, so the first place that we might hope to learn something is by looking at the properties of Higgs decay. So if I produce my Higgs, and then maybe it decays to these neutralinos. There's 2 ways that we can place bounds on this. One is indirectly, by measuring all the other possible Higgs decay modes to very high precision, and then seeing how much more we can kind of squeeze in. If we do that, the experiments find that this is essentially an invisible branching fraction for the Higgs. They find must be less than 41%. That's Atlas. CMS finds less than 32%. So, not too far off. We can also do things like directly look for these invisible decay modes. So, for example, you can have you could produce the Higgs this way. Here it would decay invisibly to the dark matter, and then the Z would decay to leptons or quarks. But you would identify this, and then you would look to see if there was any other missing energy in the event. And the limits from searches like this are very similar to what's already been found. So less than 58% is the CMS limit. And the Atlas limit's actually quite good. It's less than 29%. Yeah? Oh, so this is the invisible. So if I have Higgs to chi-chi, the branching fraction for it to decay. Yeah, so we know what all the branching fractions of the Higgs should be if it's just standard model. And right now we've measured almost all of them, but for some modes the error bars are really large. So that, because it's not precision measurements yet, there's still room for us to squeeze in other decay modes. Yeah, so the percents are just the fraction of all of the total Higgs decays. Yeah. Well, the width. I mean, kind of both, but mainly the width. Yeah, but it's not very precisely. Yeah, so so we've observed the Higgs to WW, ZZ, gamma gamma, and we also have BB bar and tau tau. So this is the ways in which we've been able to observe the Higgs. The branching fractions, the measurements of these, this one is one of the more precise. These two. These have very big error bars on them so far. Yes, yeah. Yeah, because we also know the different production modes for the Higgs. So if you assume standard model production modes, then then that gives you the fraction. Yeah. It could potentially, depends on the model. This? Yeah, if it cancels out, yeah. If it's contributing roughly equally to the production of each of these different ones, then it would roughly cancel out. But if you're seeing one of these mainly in VBF and another one in gluon fusion, then it might not. Yeah. Then I totally agree. Yeah. Yeah, I mean they do have limits on some of, they do these big fits. And they can break down limits of the couplings to fermions versus gauge bosons and things like that. Yeah. How much time? Okay, I've got a few minutes left. So let me just briefly sketch out some of the other ways we might look for dark matter. And then I want to spend the last few minutes talking about a particularly interesting class of these simplified scenarios. So another way is we can just directly produce the dark matter. So, for example, proton comes in, interacts in some way with the other proton beam, and I just produce directly the dark matter. In this case, the only thing I observe is nothing, right? Because these dark matter particles just leave the detector. So I need something else to look for, and usually what people look for is quarks or gluons that get radiated off of the initial protons. So they use that as a way of tagging these events and then looking for dark matter. Another way is to use look for a bunch of leptons. So in this case, we'd have proton, and then we could produce, for example, one of these charged guys. It would decay to a W and to a neutral one. And then the W could then decay to leptons, so you could just look for a bunch of leptons and missing energy in your event. So all of these searches, I mean, there's all sorts of variations on searches like this, and they're all ongoing, and there's a variety of different limits that, you know, if you were interested in any particular type of scenario, you could just kind of go on the CMS or Atlas webpage and look up what the bounds are. I want to focus on one other scenario just as a conclusion, because I think it's a nice way of tying in the issue of dark matter with also the question of naturalness, and whether or not this is something that we could kind of look for simultaneously at the LHC. So the last case here that I want to talk about is the scenario of colored production. So what I want to do now is argue what happens if I bring down some colored guys here. So maybe I can bring down a gluino and I can bring down a stop. Now I've increased, it becomes more complicated, right? Because I can produce more stuff now. But it's also more interesting because the colored guys, because they carry color, are produced a lot more at the LHC. So if the dark matter is coming from a decay of one of these colored guys, you would see it more easily this way. In addition, these kinds of models where I've pulled down the gluino and the stop are motivated for naturalness reasons. And that's because if we want Susie to be able to explain why the Higgs is the mass that it is, the gluino and the stop shouldn't be too heavy. And the reason for that is that they give loop corrections to the Higgs mass. So the stop gives this correction to the Higgs mass. And then in addition, there's a higher order process where I get a gluino in here and a top. Right? So if the gluino and the stop are way heavy, they actually give a very large correction to the Higgs mass, and then that, you know, we kind of built up this whole framework for supersymmetry to keep the Higgs mass light. So we definitely think that, you know, if supersymmetry is natural, that these particles, especially the gluino and the stop, should be fairly light. And I'm going to give you some numbers, but there's huge tildes on these numbers, so you kind of just take them with a grain of salt, but just so that you kind of have a vague idea that grounds you somewhere. For natural Susie, you kind of want the gluino mass to be between 1.5 to 2-ish TeV. Note the ish, it's important. And for example, the stops, you'd want to be maybe around 700-ish to GeV to a TeV-ish. Again, take these numbers with a grain of salt, but just kind of to very roughly ground you in terms of the region that's of interest. So this is definitely in reach with both the current run at the LHC and the upcoming run. And I think I only have a couple minutes, so I'm only going to show you the results, sketch out the results from one particular scenario, which is the case where we might produce two gluinos, so pair production of gluinos, and then we have each gluino decay to a as follows. So the gluino comes in, gives us a top quark, we get a stop, we get another top quark, and then we get our dark matter at the bottom of the chain. Okay? So the current limits on this are as follows, and I'll just sketch them up. usually presented on plots where we have the gluino mass on the horizontal axis and then the neutralino mass on the vertical axis. All right, this is very sketchy. Okay. Okay. So current bounds right now for this kind of topology, the limits on the gluino mass reach as high as 1.3 TeV. Depends a lot on what the mass of the neutralino is. So for example, for very heavy neutralinos, the limits are weaker just because you have less energetic final states here. But the main point is that the sensitivity of the searches is starting to hit this interesting region where we can say something about natural SUSY. And it's certainly too early right now to say whether or not, we're just kind of at the, we're pushing things. But run 2 will definitely help us to say something because it's just going to continue pushing these bounds even higher. And all of this is kind of in this interesting regime where it has implications for what we think about supersymmetry and simultaneously what we think about candidates such as the neutralino, so supersymmetric dark matter candidates. So for these kinds of scenarios, it's a nice way of kind of linking a lot of these ideas that are motivating BSM physics, both the dark matter and the naturalness ideas. Okay, I think that sort of takes me to the end. Are there any other questions or lunchtime? Yeah?
So the bound on the this should translate into the bound on the direct detection via Higgs exchange.
Mm-hmm.
So I think that this constraint in the region where the Higgs matters right now to get it is already pretty much dented.
Yeah, so I have this plot on my computer. But yeah, so if you interpret it in terms of a Higgs portal model, okay. So
you have a trilinear H chi, wherever it comes from. You can now divide and say whether chi is a fermion or
yep. Yeah.
And that's it, right?
Yeah, so the limits now, and I'm doing this from memory, they're kind of, the LHC ones come in, depending on whether or not you take it to be a scalar, fermion, or vector, kick in and really cover a lot of this light mass region. But there is a region up here where it's just, LHC doesn't say anything, but it's a nice way of seeing this complementarity between the searches. Yeah. Oh. Yeah, so the types of sort of simplified model scenarios that you would use for gravitinos would be different than the ones I've shown here. Yeah, and the searches are different because usually people, they look for searches that, I think they're mostly looking for cases where you have photons in the final state and things like that. There are searches that are focusing on that. It's a different set of...
How do you detect it?
Oh, missing energy. Yeah, the question is whether or not like you also have like other stuff that's coming out. You tend to get photons in models where the gravitino is the dark matter, so they look for that. Yeah. Yeah. Oh. Oh, yeah. Yeah. So I think this one here I was only plotting down, 600. Yeah, that was an important number to include on there. Yeah.
So the gravitino question, if you have a very light gravitino, then all of this will happen, and then there'll be a subsequent decay to the gravitino. This part of the story.
I think it depends on the model. Yeah, so you can. I'm trying to I'm not really remembering in the particular models that people have actually set limits on. But yeah, so you can. I think you can have scenarios where you'd have something like this, and then the gravitino comes out at the end. If you just make the decay chains longer, right? Where did? oh, here. Yeah, so if you just make these decay chains longer, what tends to happen is you get more visible stuff. And, you know, you could just search for that additional, yeah. Yeah, yeah, yeah. Right.
Thank you for a great series.
Oh, sure, it was a pleasure.